All right. Let's go ahead and get started. Hi, everybody. All right. How was the project? Everybody get their projects done? Did any questions come up during the execution of your project? Yes? That you didn't get answered yet? Yes? Huh. That's bad. Did you look at the sample code and that I put out? List-e set over to? Okay. That's a hack, but it probably works. All right. I posted the topics for the final exam. Probably nobody really looked at it because you were busy finishing your project, but does anybody have questions about the topics on the final exam and what to expect? Did anybody actually look at it yet? It's okay if you haven't. I just, because you have time before the final exam, it's like a month from now or something, right? When is the final exam? Now, did you take that off of mine or did you look at the registrar's page for that? All right, good, as long as you check, because I have gotten the final exam time wrong on the syllabus before, so now I put it up there, but I just tell everybody that you have to check yourself. So, I will not be in my office next week. I will be out. So if you have questions next week, I might be available by email. For the final exam, the TAs are going to hold review sessions. Look on Blackboard for the time and locations of those. Essentially, you show up and they will, I don't know what they do, but students like them. They give you all the answers to the exam or something, which isn't written yet. I will be in the office the 16th and 17th, the 2 days before the exam, probably, barring getting run over by a bus or something like that. I should be around. All right. Any other questions? So yes, I forgot. I meant to do that. I'm going to, just like I sent you out the midterm that I used before, I'm going to give you the final I used last year. How's that? But if you email me and remind me, I'll remember. And if you don't, I may or may not. So it is in your interest to email me. Somebody who has a computer is probably emailing me right now. Yes? Yes, in the description of the final exam, I say what's going to be on there, and it's pretty much mostly covers the second half of the semester. That being said, you have to know the stuff from the first half of the semester because it's got classes and loops and functions, variables, stuff like that. So. Yes, sir. Yes, that's what she just asked. It's mostly on the second half of the semester, but you have to know the stuff from the first half. Otherwise, you can't just forget it. So it is cumulative. It's more focused on the second half. And anybody already emailed me? Okay, good. Then I will send out the final exam from last year that you can use to study from. And then I get to write a whole new one, which will be fun. Okay, so last time we were talking about recursion over linked lists, and I had to hurry through my example, and I didn't like that. So we're going to talk about it more. But first, let's refresh our memory. What do we need for recursion? Sir? Okay, so there's two important things for recursive problems. We need a sliceable problem, something that we can take a little piece off and process, and then process the rest of the chunk. And we need a base case, which is we need to know when to stop, right? Sometimes it's obvious when you slice the thing and it's all gone, but other times the computer will just blindly run on and do things forever, which is bad. How many of you all during the Project 5 had your program just hang, where you'd run it and it would just sit and do nothing? Pretty much everybody? So what was it actually doing while it was hanging? It was actually doing something over and over again. Most commonly, you had a loop in your linked list. So instead of being a nice straight line, it was a loop, and you started going along the list, and it just kept going around and around and around. Very, very common. So, so you need to know when to stop. So, boy, is that sort of visible? Maybe I should turn out the lights up front for a second. So what I've done is I've actually drawn pictures this time. So instead of me drawing on the board, that's exactly the opposite of what I wanted. I don't know. Is that readable? Okay. So I put the code in two segments. The first segment is the code that actually creates the linked list, and we'll step through this quickly, and then we'll look at how the recursion works on the linked list. This code is copied from the handout that I gave you. It's also posted on Blackboard in the file recursive something list something. So, but it's in there. You can look through and find it. So here's a code that builds the list. And if we step through, we start at int main, which isn't on the screen. We create a head pointer called null. We create a current pointer also, a head pointer set to null and a current pointer also set to null. We do some stuff to open the file, and then we start inputting things into an integer. This is slightly different than how you did it for your project, but you should understand what's going on. So the first step, we set current equal to a new node that has an integer, and the first integer we read is 16. So we create a new node and set it to 16. Any questions on this? You all should be familiar with this. The next step, current set next node head. Whoops. Well, we do that, and setting current set next node to head results in nothing because head is null. So we're setting this pointer inside the node to null when it's already null. Are you good with that? The next step, head equals current, and we flip the head pointer to point at the current node. Go back up to the while loop, input into an integer. Current equals new node integer. So current now points at a new node containing an integer. Do y'all feel that because you did this for the project, you have kind of a handle on it? Yes? How many say yes? How many like me stepping through it just because it's fun? Great. It's fun for me too. So here we are. Current is now pointing at this new node. The next line, current set next node to head. And we flip the pointer inside the node to point at the head node. And then finally, we flip current around to point, finally we flip head around to point at current. We now have a linked list, right? We had a linked list all along. What's this right there? A pointer to, which is also an empty linked list, right? What's this right here? A pointer to. It's a pointer to a linked list. What is head here? It's part of a linked list. What is current here? Part of a linked list. Okay. Remember, we have sliceable problems. All right, the next item comes along. It gets loaded into the integer. Current equals set next node. And current equals new node with an integer of 2. Right? Everybody with me? Who's against me? All right, so we create the current. It has 2. We flip the pointer inside current to point at the head node, and then we point the head pointer to point at the current node. So every time we read something, we're adding a node and putting it on to the front of the list. We do it again. We create a new node 4. Current points at the new node containing the value 4. The pointer inside that node switches to point at the head pointer. And then finally, the head pointer switches to point at current. 3 steps. Thumbs up? You all are quiet today. Are you sad that class is ending? All right. There's more numbers. We read a 1 out of there. 1 gets put in a new node. The pointer inside the node points at head. Head points at the new node. At this point, I believe we have completely constructed the list, right? We have a linked list, head to 1 to 4 to 2 to 8 to 16. We also have a linked list inside one that's 4 to 8. We have a linked list in here. Every single one of these pointers is the head of a linked list, which we're going to use when we talk about recursion, right? Sir? Yep. 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 It's a pointer to a node, but there happens to be no node at the end of that pointer, so it is an empty linked list. Does that make sense? This here is a pointer to a node. It has 1 item on the linked list. This one here is a pointer to the node. It has 2 items on the linked list. Right. And we're going to use this fact. We're going to use the fact that each one of these things in here is a pointer to a linked list to do recursion, because we can slice the top one off and then process the rest recursively. Yes? Maybe instead of candy today, I should have brought like caffeine. You're all looking a little draggy. I had a list of ideas over there for the last day, mechanical bull and musical guests and stuff like that, but I didn't really have time to get it all done. So, all right. So now we're switching over to the part where we do things recursively. And I didn't put all the code on the board, but one of the things that happens is we create a new pointer called thing. And this thing pointer is going to return the result, is going to store the result of all the recursive calls to do something. So originally in the code, we call this do something function, giving it the value of head. So here's what happens. The first time it's called, the function do something is called, and the parameter in their list, which is this parameter right here, points at the same thing head points at, because head is the initial parameter in the code. Everybody good with that? Any questions? I'm going to make sure you have a chance to answer your questions because, you know, if I go through something in this detail, it would be a great thing to put on the exam, right? Or a great thing to have you study and not put on the exam. One way or the other works for me, whichever you prefer. Questions? Okay. So I didn't put all the code on there, but if you look at the sheet that I handed out, there's a call that says do something head. And what happens is the value of head gets copied into this pointer list right here. And because head points at the first node, list is also going to point at the first node. Now let's step through, given that we have list pointing at something. Is list equal to null? How many of y'all think it is? How many of you think it's not? How many of you are unsure? Okay, list is pointing at something. It's not pointing at 0, so it is not null. The way I've diagrammed it is anytime something points at 0, I put a little square edge thing there on the end. So it's not pointing at null. If list get next node equals null, is this true or false? Why? All right, so we go to list, we follow the arrow, that's what the arrow operator means, and we say check get next node. So we're right there in this pointer in the node entitled with the number 1 inside. Is that a null pointer or not? It is not because it points at the node containing 4. So this is not true. Next node equals null is not true. So here's what we do. We return the value from calling do something on list get next node. So we're calling do something again, except instead of this time passing at the head pointer, we're passing at this pointer here that's right inside node with 1. Everybody see that? So here's what happens. We get another instance of the do something function, another instance of it. Every time we recurse on a function, we get another copy of the function. All right? Make sense? And where does the list, it's got a variable, the same name, but a different variable named list, and where is that pointing? It's like I broke your spirits with Project 5. Good Lord. Did I? What? Well, you're not rioting. I don't feel threatened yet, so I don't think I did that bad. If you ever want to see a really bad project, go back and look at the project. And it was like 2003 or something. It was the Starfish project. All the current students who ever did the Starfish project have graduated. But for years, like the Starfish project was legend. It was a legend. People are like, "Oh my God, you were in the Starfish project class?" It was insane. It was an insane project. It was absolutely nuts. It was a simulation of the predator-prey relationship between starfish and barnacles on an island. So instead of just having a linked list, you had a circularly linked lists. And then, like, as the starfish ate the barnacles, they would move from like one place to the other, but then the barnacles would grow back, and then the populations would wax and wane because, like, if they ate all the barnacles, the starfish would die. And then when the barnacles came back, the starfish would like have a lot more to eat, so they'd reproduce more. And then there was like a graphing thing where you could graph like the cycles of each over time. Yeah, it was 071. Yeah, it was 071. It was a little bit too challenging. I spent like 3 days I spent a full day doing nothing but answering emails and debugging students' code. I answered over 1,000 emails that day. I just woke up in the morning and started answering emails, and I answered them until like 1 in the morning because I felt so bad about giving hard project. But anyway, All right. Now that maybe you don't feel so bad, you can go back and look at it. Actually, out of the entire class, only 3 students completed it out of like a 40-person class. So it was a little bit too hard. All right. All right. So now that maybe you don't feel so bad about the horrible things I've been doing to you, here we are. We have another recursion on list. So we have another copy of do something that points at that. And again, we do exactly the same thing. Is list equal to null? Is list equal to null? Everybody say no. Okay. Is list get next node equal to null? Why not? Follow it, look there, it's not null. Great. So what do? We recurse. We call the do something function again, this time with the pointer that points from node containing 4 to the node containing 2. Here we go again. A new copy of this, a new list variable that is now pointing at the node 2. Is list equal to null? Is list equal to null? Is list get next node equal to null? Great. What do? We look at it and we say, hey, we need to return do something list get next node. So now we're calling it with the pointer that points at the node containing 8. All right. Let's step through this again. Is list equal to null? Is list get next node equal to null? So what do? We call it again. Return do something get next node. All right, here we are. One last time. Is list equal to null? Is list get next node equal to null? Yes, it is. So now finally we're going to do something different. What are we going to do? All right, we are going to return as a function, as a value, this pointer. Okay, we're going to return that. Now I didn't make an explicit return variable in this example. I will next time I teach it. But here's the value. We get a return value, and it's returning this pointer, the pointer to node 16. No, it returns the address of 16. It returns a pointer to that node. So the thing that's getting returned is not this node, it's that pointer, which is the address of the node that we're interested in. Okay. And here's what happens. That function goes away. And because we're just returning this, right, here it says return do something, right? This do something figured out it was the value of 16, and it pops back up to here. And we're going to return the result of this. And what is the result of this? It is the pointer that points at node 16. So it's kind of like we have a whole bunch of returns in a row, one for each function, and each time it's going to return the thing that returned before. Does that blow your mind? Yep. We'll do it again. So we finally figured out, and we figured out the thing that we're returning is this pointer right here that goes to node 16. And no, the node inside node 16 points to no. But this pointer right here, this pointer from the do something function to 16, which was the list pointer, points at node 16. Okay? Everybody with me? Yep, because what we got is once we get down here, list get next node equals null, we'll return list. And list, and let me just go back one slide, whoops. List was pointing at node 16, so we're returning what the value was, which is the pointer that points at 16. So we start returning thing, and the first thing we return is this pointer to 16. Now what happens is this whole call, do something, arrow, get next node, becomes the thing that was returned. And what is getting returned? The pointer to 16. This thing right here is our return. So what happens is in the function above, right here, this whole call gets replaced by the thing that's being returned, whoops, which is the pointer to node 16. Because each time we did this do something, we did return do something list get next node. So it's kind of like we have return, 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 and then list once we've gotten list down to the right point. Okay, who's with me? Who's not? what's happening is do something. Once do something completes, right here we say return list. This, the last version, let me just go back a slide or two. This last call to do something finally just returns something. We've reached one of our base cases, right? We have this base case where list get next node is equal to null. So now we can actually start returning something instead of recursing. And the thing that we're returning is this pointer that we found. The thing that we were looking for is when you find something on the list that the get next node is null, then you start returning. We've gone down. In this one, we went to the else. And this one, we went to the else. And this one, we went to the else. This one, we went to the else. And this one, finally, we did not hit the else. We hit that return. Yep. And so when we start returning, it returns back up. Sir? That's what's going to happen is when we're done, it's going to pass this pointer all the way back up. And that'll be what's returned each time now that we've found it. Yes, I'll draw that when we get there. Yep. Yes, we do. And the reason is because if you were to call this function on a null list, it would crash if you didn't have that in there. Because the first thing that would happen is you'd say list get next node, it would say null gets next node, it would crash. So this handles the case where the list is empty, which we're not seeing in this example, but it exists in the real world. It would crash without this if statement if it was called on null. Okay, who's happy right now? Who's unhappy? Who's at least happy the class is over? We're going to be done in like 10 minutes, I swear. Seriously. Well, you're not leaving, but we're going to be done in like 10 minutes. So, all right, does that make you happier? I'm trying, give me credit for trying up here. All right, so finally we're going to start returning this value. And we're returning the result, returning to this, right? This do something made the call return do something. And this do something returned list. So this whole return statement here becomes the thing that was found before, which is list, which is the node that's pointing at 16. So what happens is each time we're returning, we return all the way back up the stack, one step after another, until we get to the top. And the thing that finally gets returned is that thing is equal to the result of the function call. So thing ends up pointing at the very last node on the list. So what do something should have been called instead of do something is what? Yeah, find last node. Because it tells you which the last node on the list is, and it finds it recursively. All right. What can I do to explain this better? What are you just wishing this was over now? How are you all doing? Tell me. Yes. Yep, because each time in the else statement we were returning the result of do something. And so each time do something finishes and it returns to the return statement before it, which returns to the return statement before it, which returns to the return statement before it. So once we start returning, we're just returning the result that was found by the next call, recursive call. Yes? Yep. Nope. Nope. There's different types of recursion. There's what's called head recursion and tail recursion. And so I'm just giving you an example of one. You will get more recursion in the future. I can guarantee you. I'm just supposed to introduce it to you on the last few days so that I can thoroughly confuse you and demoralize you and baffle you. Yes? This? If it's there just in case, like you call it with an empty list, right? So if the first time, if you ever accidentally somebody says, hey, here's an empty list, tell me where the last thing is. There is no last thing on an empty list. So we have to have some way of indicating that. So that's why it's there. Yeah? Mm-hmm. Here's what you would change. Are you ready? If you wanted to find a specific node on the list, instead of saying list get next node equal null, you would say something like list get data equals whatever the hell you're looking for. It would be identical to this. Absolutely identical. Except all you would say is instead of checking to see if the next node was not null, you would say if it's equal to whatever value you're looking for. Yep. Mm-hmm. Each time it would look in there. I don't quite know what you mean by that. Yes? Do you have a question? No. You would definitely need to have this. You would definitely need to have that because you might iterate and eventually end up on a null spot and never find anything. But if you wanted to make this such that you were looking for a particular value in there, you would just change this line, list arrow get next node, to list arrow get data equals, and then whatever value you're looking for. Does that make sense? So, and the other thing you'd have to do is when you passed in the parameters, you'd have to pass in the list and the value that you're looking for. So the function would have two parameters, the list to search on and the thing you were looking for. Which is a good exam question, by the way. All right, everybody good? Any last questions about recursion on a linked list? Yes? So I will send you the final exam from last time and you'll see. Typically what I do on the final exam is I have a question that builds a list, either from the front or back, so you can see how it's built. Then I do some random pointer stuff on it, just whatever I happen to feel like, and then I ask you to draw the results of that random pointer stuff, and then I ask you to tell me if there are any dangling pointers or memory leaks as a result of the random things that I do. So that's, to be honest, that's one of the questions I normally do. And then you have to draw the linked list at each point so that you can show me that you understood the operations. And then I might have some other linked list things where I'll give you a function that operates on a linked list, and I'll say, what is this output? And I'll expect you to trace through and tell me what it outputs. I won't have you draw the structure at each point along the way. So, all right. Sir? In some cases, it is equivalent to using a while statement. In some cases, it is worse. Sometimes, however, it can very much simplify how you approach a problem. There are recursive solutions to problems that are much, much easier than iterative solutions to problems. Now, I'm not going to give you an example of what those problems are, because if you keep going in computer science, you will, I would probably say encounter them, but the correct answer would be buried in them at some point. So, because you will get plenty of those as we go on. The whole point of me teaching you this is that when you call something recursively, you get multiple copies of the same functions, that they have the same variables inside, but they represent different ones. And then as things return, data gets passed back up through the series of calls. Okay, and recursion has two things, what? And sliceable problem, okay? The rest you'll learn about later, because there's a lot more to it. A lot more. Didn't I mention that there are entire languages that are entirely recursive? And they're awesome. They're fun. Yes. Today, this class, by the way, is like, it feels like it's drinking from a fire hose, doesn't it? Like just stuff comes out. But it's really like, you know, taking a sip out of a very large barrel, because there is a lot more to learn, which is, you know, there. So, I don't know. Maybe that's a bad analogy. I'm not quite sure what to do there. So, all right, let me just go through this. All right, any last questions? The end. That's the end of the class. That is the end of all the material we are learning before oh, that one thing, the final exam. So, I have a confession to make. I've been saving this for the last day. Maybe I should do this by email, but I'll just go ahead and tell you something. I was harder in this section of the class than I have been on many other sections of class. And you might want to ask me a question, why? Anybody want to ask me? You might be thinking it's just because I'm like a dick, but that is not the right answer, okay? The answer is because this is the foundation for like a whole education in computer science. And because most of you, if not all of you, I guess not all of you because a few others snuck in, because most of you are freshmen and because most of you might be moving forward in computer science, I wanted you to have a very strong education, a very strong foundation before you move forward, okay? So I gave you projects that were a little bit more challenging than I have given, though not up to the level of the Starfish project. You can go take a look at that if you want something to do over winter break. If you're here in this class today, you are completely and totally set for the upcoming classes in computer science, okay? You are ready. I have absolutely no doubt about it. You're also a really good class. I appreciate you laughing at my jokes and, you know, eating my candy and stuff like that. And one last reminder, I really teach because I enjoy it. I mean, I'm here teaching because I like teaching, and I like teaching because I like you as students. So I hope that you all stay in touch. You know that I have office, I have a sofa, come by, say hi, I probably have candy. I also like eating at Leo's. I know that you all hate it because you eat there like all the time, but like once a year or twice a year, students will be like, hey, let's go to Leo's, and I am happy to go to Leo's and like bake my own pizza. They never had that when I was an undergrad. So that makes me excited. The one last thing we need, can you just open the door and back and tell those people standing up that they can come inside? The one last thing I'm going to need from you is your feedback. Now, this is kind of unusual, but you might have noticed over the course of the semester that I've been doing like video and audio, and we did the flipped classroom where you watch videos before we came in and stuff. This is an experiment to like figure out how to teach the class better. And these folks, Mindy and Sarah, right, are going to talk to you about the class, your feelings about the class, how we can improve it for next time in the future, and I hope that you will give honest and complete feedback. I'm going to leave so that I am not here to influence like your feedback or feelings, and also because I'm lazy and I get like half the class off and I get paid anyway, so it works out really well for me. And they are going to take over and guide you through some stuff to help us improve the class for next time. Thanks very much. See y'all later. Have a good break.